For over a century, one of the absolute cornerstones of modern physics has been treated as, well, an unprovable assumption, a postulate we all just had to accept. But what if it isn't? What if we could actually prove that the speed of light is constant? Okay, let's dive right into this.
It really all comes down to this one huge question. We're always told nothing can go faster than light, and that its speed is the same for absolutely everyone, no matter how fast you're moving. But why? I mean, that idea clashes so violently with our everyday common sense that it sounds almost like magic.
So to really see just how deep this conflict runs, we've got to compare our intuition, the stuff that's based on classical mechanics, with the seriously strange reality of how light actually behaves.
Okay, so imagine you're inside this spaceship. There's a device right in the middle that fires two bullets, K1 and K2, at the exact same speed. As you'd expect, you see them hit the front and back walls at precisely the same time. Simple enough, right? But what about someone watching all this from the outside?
Well, for that outside observer, the ship is moving. So the bullet fired forward seems to be moving faster. You add its speed to the ship's speed, and the bullet fired backward seems slower. But, and this is the key, the forward bullet also has a longer way to go because the front wall is moving away from it. Under the good old rules of Galilean physics, these two effects perfectly cancel each other out. So both you and the outside observer agree. The bullets hit the walls at the same time.
And here is where reality just takes a massive left turn. If we swap out those bullets for photons, for beams of light, you'd think the same logic applies. The outside observer should measure that forward light beam speed as c plus the ship's speed. But they don't. Experiment after experiment has confirmed they measure its speed as just c. And it's the same for the beam going backward. The speed of light simply refuses to add or subtract.
This leads to a result that just completely bends your brain. Since the light speed is locked at c for that outside observer, but the front wall is still moving away, that forward photon absolutely must take longer to get there. An event that was simultaneous for you inside the ship is not simultaneous for the person outside. This just shatters the classical idea of a single absolute time flowing for everyone.
So this table really just boils it all down. For things with mass, like our bullets, speeds add up like you'd expect and simultaneity is absolute. But for light, speed is stubbornly constant, which forces simultaneity to become relative. This was the fundamental contradiction that had physicists completely stumped.
So, faced with this seemingly impossible paradox, the scientific community had to make a choice, and it was a choice that would define physics for the next 100 years.
Back in 1887, the famous Michelson-Morley experiment proved this wasn't just some fun thought experiment. The speed of light in a vacuum really is constant, no matter how its source is moving. And since they couldn't figure out how to reconcile this with Newtonian mechanics, physicists essentially said, okay, we can't explain it, so we're just going to accept it as a fundamental rule of the universe. The anomaly became a postulate.
And this quote from the source material just gets right to the heart of it. The entire theory of relativity was built on top of this assumed incompatibility. It was a brilliant, world-changing theory, but it all started with the idea that Newton's laws and the behavior of light just couldn't play nice together.
But what if that core assumption, what if that assumed incompatibility was just plain wrong? What if it was never really there to begin with?
Okay, let's get to the main event here.
This right here is the paradigm shift. Instead of just blindly accepting the constancy of light as some unexplainable starting point, we're going to see if we can actually derive it, prove it, using the very same laws of classical physics it was supposed to contradict.
Now, this isn't just some wild idea we're pulling out of a hat. This entire argument is grounded in the incredible work presented in Chapter 14 of the book Newton and Relativity by Sester, Clementi, and Korff. They went back and re-examined the first principles, and they came to a truly stunning conclusion. And this is the absolutely crucial point. The main tool we're about to use, this thing called the relativistic velocity addition formula, wasn't just invented for this purpose. As you can see here, the previous chapters of their book derive it, step by step, purely from classical physics. And most importantly, its derivation never assumes that the speed of light is constant, and it doesn't use the Lorentz transformations. This means our proof won't be a circular argument. It's a clean, independent test.
All right, with that really important foundation laid, let's actually walk through the proof itself. It is, and I mean this, surprisingly elegant.
So here it is, our key. This formula, Relation 11.6 is what you get for adding velocities when you properly emerge from classical conservation laws while also accounting for mass-energy equivalence. And because of those independent origins we just talked about, it is the perfect, unbiased tool to test how light behaves.
Okay, let's set it up. We want to find out the speed of light as measured by our outside observer. We'll call that VL. So, in the formula, we replace V1 with c. That's the speed of light from a source that's not moving. Then we replace V2 with VQ. That's the velocity of our moving spaceship, our moving light source.
Now for the fun part. Let's solve it. First, just look at the denominator. We've got c times VQ divided by c squared. Pretty simple. One of the c's on the top and bottom cancels out, which simplifies that little term to just VQ over c. Easy enough.
Now, to combine the 1 and that VQ over c, we just need a common denominator, which is c. So that gives us a new denominator of c plus VQ all over c. So now look what we've got. We have a fraction on top of another fraction. And here is the beautiful part. When you divide these fractions, you have a c plus VQ term in the numerator and another c plus VQ term in the denominator. They are identical. They just, poof, perfectly cancel each other out, reducing to 1. So what are we left with? Well, that c from the very bottom of the stack flips all the way up to the top. The final, undeniable result is that VL equals c. It doesn't matter what the velocity of the source VQ is. It could be anything. The equation always resolves to c. The speed of light is constant.
So what does this all mean? I mean, it's more than just a cool math trick. We've just witnessed a fundamental shift in how we can look at the universe.
This slide really just puts it all together. The constancy of the speed of light isn't some strange exception that we need a special postulate for. It's a mathematical consequence that flows directly from classical physics. It means the Michelson-Morley experiment wasn't some shocking anomaly. It was the experimental confirmation of a law that was kind of hidden in plain sight the whole time.
This whole thing reframes one of the biggest ideas in science, not as a leap of faith, but as a provable theorem. And that leaves us with a pretty fascinating final thought, right? If the most famous postulate in all of physics turns out to be a provable law, what other fundamental ideas are we just assuming are true, waiting for someone to look at them in a new light?